Number 8 is a non-homogeneous equation. And I notice here that we have 3 derivatives. So I would say, let's start with let x1 equal y. That's always the case. If I take a derivative, and I'm going to call this x sub 2. I need to go all the way to x sub 3. Now if I take a derivative of that, x sub 2 prime, which is y double prime, there's no y double prime in there, which is x sub 1 double prime. I'm going to call this x sub 3. Now I'll keep on going until I have a third derivative in there. If I take a derivative of this, that would be x2 double prime, which equal y triple prime, which is x sub 1 triple prime. So if I really look at this, I have a third derivative in terms of x1 prime. I have a second derivative except in terms of x sub 2 prime, and I have a first derivative in terms of y1 prime, and of course the function itself. So if I really look at this, I know for sure how this is going to work. This is really x, let me see how that works. That's x sub 3 prime minus dy dx y prime. Isn't that x sub 1? Y prime x sub 2 plus y. Isn't y x sub 1? And that's the cosine of t. So I want each of those to be in terms of one derivative so that I could write the derivative vector. So now I could say, well, alright, then I could take this differential equations and I could write it as, again, in normal form, I could write it as x1, x2, x3. So you always need that many variables. Prime is going to equal, and now just the part I want to really get used to, times x sub 1, x sub 2, x sub 3, plus, since I have a cosine, and the way it works, I'm just going to move those a bit to the right because they're kind of squished together. Here we go. So if I start glancing at this, the bottom is the easiest. The bottom one, x sub 3 prime, is actually x sub 2. So x sub 3 prime is actually x sub 2 minus x sub 1 plus cosine of t. Cosine of t is right there. I got it. And if I want to get negative x sub 1, shouldn't I put a negative 1 there? And a positive x sub 2, should I put a 1 there? And no x sub 3. I got it. Now if I go to the actual coloring, and that's pretty much how it works, I want x sub 2, and that would be x sub 2, that is 0, x sub 2 prime, what is that? Okay, there we go. X sub 2 prime is x sub 3, 0, 0, 1, and x sub 1 prime is x sub 2. There you go. And you go in that order, always. x1, x2, x3, and there it is. And again, this is x prime equals ax plus f of t. And of course, that's a 0 and that's a 0. And that's how it works. Again, it's going to take a bit of time to get used to this. We go forward and we go backwards. So either they give us the equation, we come up with the system, they give us the system, we come up with the equation. And if I look at this, it's fairly simple to go in this direction. Write the given system as a set of scalar equations. That's very simple to do. You would say simply x sub 1 prime equals 2x sub 1 plus, maybe I should write that down for you. This really says x sub 1, x sub 2 prime equals 2, 1, negative 1, 3 multiplied by x1, x2 equaling oops, plus. Plus, this is really t e to the t and e to the t. So if I really want to write it out, I'm going to say the system of equations x sub 1 prime is going to be 2x sub 1 plus x sub 2 plus t e to the t, and x sub 2 prime is going to be negative x sub 1 plus 3x sub 2 plus e to the t, and that would be the actual system of equations. And if I proceed and do number 12 after that, which is almost identical, again, it's really easy. Here we have x1, x2, x3, so it really says x sub 1 prime is going to equal, and this is going to be x sub 2 plus t plus 3, x sub 2 prime, actually x sub 3 prime. I don't know if I should, you know what, let me show you that. So you know what, let me finish it first and then I'll show you. X sub 3, x sub 2 prime, what just happened? X sub 2 prime is going to equal x sub 3 minus t plus 1, and x sub 3 prime is going to equal negative x sub 1 plus x sub 2 plus 2x sub 3 plus 2t plus 0. This is again saying 0, 1, 0, 0, 0, 1, negative 1, 1, 2, and that is x1, x2, x3. And you could figure out kind of how we're doing this. Once you get the hang of this, it's not that bad. You could move forward and backwards. Of course, moving back turns out to be taking a differential equation and transforming that into a normal system is a bit more work. And behold, the famous Wronskian holds, but it's a bit different than what you used to, slightly different. And let me get that out of the way. Definition 2, if you're given the column vectors, then what you do, you list those vectors. No derivatives, you just list them out, and you find the determinant of that. That's the Wronskian. And if you recall, if the Wronskian does not equal 0, then they're linearly independent. Alright? And 14 and 16, determine whether the given vector functions are linearly dependent or linearly independent. What you do, you find the determinant for t e to the negative t. And that's a Wronskian. And that would be t e to the negative 2t minus e to the negative 2t, which really doesn't equal 0, because exponentials can never equal 0, therefore linearly independent. And if I do number 16, the same deal. I don't want to do a 3 by 3, it's just busy work for no reason, we just want to get an idea. The Wronskian of that would be, and you would list the sine of t, the cosine of t, the sine of 2t, and the cosine of 2t, and that would be the sine of t cosine of 2t minus cosine of t sine of 2t. This is twice the sine cosine squared of t, and since that's sine cosine, I have 3 identities with the cosine. I'll stick with the one with the cosine. That's twice cosine squared of t minus 1. That is twice the sine of t cosine squared of t minus the sine of t minus twice the sine of t cosine squared of t. That is really negative the sine of t. That's not always 0. That's 0 only if t equals certain values, therefore linearly independent. So it has to be always 0. This is not always 0. And if I take the last problem, the given vector functions are solutions of this equation. Determine whether they form a fundamental solution. So they're telling you this is a solution and this is the solution. Determine whether they form a fundamental solution. So what do? You figure out the Wronskian. The Wronskian of t is really the determinant of 3e to the negative t, 2e to the negative t, and e to the 4t and negative e to the 4t. And that would be negative 3e to the 3t minus 2e to the 3t, which is negative 5e to the 3t, which can never equal 0, therefore linearly independent. Here I should have said linearly independent as long as t doesn't equal 0 plus pi k. Right? T could be anything. So here it's dependent on... So here we go. Got it. So the given vectors are solution. Determine whether they form a fundamental solution set. Remember fundamental solution set? This has to be a solution. This has to be a solution. And they are linearly independent. Right? If they do, find a fundamental matrix for the system and give the general solution. Well, the fundamental matrix, kind of like the fundamental set in this case, is going to be simply 3e to the negative t, 2e to the negative t. Come on. e to the 4t and negative e to the 4t. And the actual symbol, why is this? Oh, it's shifted down way too much. And the general solution, I think you're going to like this, is C1 times 3e to the negative t, 2e to the negative t, plus C sub 2, and hopefully you've seen a pattern in what we did back in the days and what we're doing right now. Any multiple of those will do. That's the solution, and that's the fundamental matrix. Fundamental matrix would be the list of the vectors, kind of like when we did back in the days, if you recall, listing the two vectors down. He said that's a fundamental set, and y was C1 times a multiple of the first, plus C sub 2 times multiple of the second. And there's your homework on this section. Oops. There's the homework on this section. And that concludes it.